Hi there, welcome back to the undergraduate mathematics seminar. We're glad to have Claire Zhang and Zhekai Peng here, who are going to tell us about matrix analysis with an emphasis on inequalities. This is a project with Mike Cavers, and I'm very excited to see what they have to say today. Thanks for coming out, everyone.
Yeah, thank you, Parker. And in today's presentation, Yuhong and I are going to present some key results in matrix analysis, and we will in particular focus on matrix inequalities. So we want to first thank Professor Michael Cavers for the supervision during the study. And we will begin the presentation with a review of definitions and facts in linear algebra. So first, we define a matrix A to be symmetric if A transpose is equal to A, and also a square matrix A is orthogonal matrix if A transpose is equal to A inverse. And then there's a theorem about spectral decomposition for symmetric matrices. So if A is a n by n real symmetric matrix and lambda 1 to lambda n are the eigenvalues of A and V1 to Vn are the corresponding eigenvectors, then we can write A as P lambda P transpose, where P is a matrix consisting of eigenvectors and lambda is a diagonal matrix with eigenvalues on the diagonal entries. And the remark is that since here A is equal to P lambda P transpose, like the matrix P above has to be an orthogonal matrix. And if in general we write P lambda P inverse, then it might not be the orthogonal matrix. It can be other P. And then we introduce the definition of non-negative definite matrix and also positive definite matrix. So n by n real symmetric matrix A is called non-negative definite if the quadratic form X transpose AX is always non-negative. And the definition of positive definite matrix is a bit stricter. So we require X transpose AX to be positive for all non-zero X. And then there's two equivalent definitions, or we say there are theorems. And so if A is a non-negative definite, then like it's if and only if all the eigenvalues are non-negative. And similarly, it's positive definite if and only if all the eigenvalues are positive. Also, in some textbooks, they write positive semi-definite instead of non-negative definite. And then let's look at an example. So let A and B be two n by n real symmetric positive definite matrices, and we let K1 and K2 be two positive real numbers, and let C be the linear combination of A and B. Then we have the conclusion that AB inverse A, C, and C inverse are all symmetric positive definite matrices. So other parts are not difficult to prove and are left as an exercise. So we only prove AB inverse A is positive definite. So here we know A is real symmetric positive definite. So the eigenvalues are always positive. So the matrix A is non-singular, and thus it's full rank. So this implies that A has a trivial null space. And since B is also positive definite, the inverse of B is also positive definite. Thus, in order to verify that AB inverse A is positive definite, like we consider the quadratic form X transpose AB inverse AX. And then since A is symmetric, we can write it as AX times B inverse times AX. And also B inverse is positive definite. So this term is equal to 0. It's always greater or equal to 0. And A has a trivial null space. So this equals to 0 if and only if AX equals to 0, and if and only if X is equal to 0. And this completes the proof that the matrix AB inverse A is positive definite. And then after defining positive definite matrix, we are able to define the matrix square root. So let A be a positive definite matrix. Then the square root of matrix A is P lambda inverse, P lambda, the square root of lambda times P inverse. So an example is the following. So we let A be the matrix 10, 6, 6, 10. Then we can compute the eigenvalues and the corresponding eigenvectors. So lambda 1 is equal to 4 with eigenvectors negative 1, 1, and lambda 2 is equal to 16 with eigenvectors 1, 1. And then by the spectral decomposition of matrices, we know that we can write A into this form. And we also know that square root of diagonal matrix is taking square root of each entry on the diagonal. So 40016, the square root of it is just 2004. And then we compute the square root of A. We do the matrix multiplication, and finally we know it's equals to 3113. And later there's a theorem saying that if A is a positive definite matrix and consider its positive square root, and also we consider like the inverse of the square root, then we have the conclusion that the matrix square root is symmetric. And also if we times the square root with itself, we get the matrix A. And if we multiply the square root with its inverse, we get identity. And if we multiply the inverse of the square root with the inverse of square root, we get the inverse of matrix A. And then
next, I will introduce another important kind of matrix, which we will use in further matrix inequalities, which is the Hermitian matrix. A square matrix A is Hermitian, or in other textbook, we call it self-adjoint adjoint matrix if A is equal to A star, means it is equal to its own conjugate transpose. So here's an example. Let A be a 2 by 2 matrix, which is 1, 2 plus I, 2 minus I, and 2. Then we take the complex conjugate of A, which we got 1, 2 minus I, 2 plus I, 2, and then we take the transpose of its complex conjugate, and we have 1, 2 plus I, 2 minus I, and 2. So we can easily find that its conjugate transpose is equal to the matrix itself. So we have A star is equal to A. So A is a Hermitian matrix. Note that if A has real entries, then A is Hermitian if and only if it is a symmetric matrix.
So this is the end of the review of linear algebra. And before moving to the matrix inequalities, let's first look at an interesting matrix equality, which is Woodbury matrix identity. So the Woodbury matrix identity can be used in a lot of fields. So we sometimes use rank K correction when new data is added to a model. And by using the Woodbury matrix identity, we can do a rank K correction to the inverse of the original matrix in order to compute the inverse of a rank K correction of some matrix. So we let A, X, R, Y be the complex matrices with the size n by n, n by r by r, and r by n respectively. And we also suppose that AR and A plus XR, Y are all invertible. Then we can have the this formula. And for the rank K correction, so I want to explain it in the context of this equation. So here A is a known data matrix. And when we add a rank K matrix XR, Y to A, we can see from this equation that like the inverse doesn't change a lot from A inverse, because the longer term A inverse times X times the R inverse plus Y A inverse X inverse times Y A inverse, we can see that it is also rank K. So it only differs from by a rank K matrix. Yeah, and then let's see the proof. So the proof is multiplying A plus XRY to the right-hand side. And we expand it to be like I plus XRYA inverse minus those two other terms. And then we notice that the later two terms can be factored into that form. And also we take XR out, and the middle two terms are inverse of each other, which is R inverse plus YA inverse X times its inverse. And then they got canceled, and finally we get the identity matrix. So this is an identity that is useful to compute when we add a rank K matrix. And it has some application in statistics. So remember that, for example, in linear regression, we need to make sure that the matrix has a full rank. So when we add some new matrix, sometimes we need to use this identity to make sure like the rank matches. And then there's a corollary. So when we consider the special case that all the matrix has the same size and also X and Y are identity matrix, then we can get a simplified formula, which is only compute A plus R inverse. And we plug it into the identity. So, and with some simplification, we can find out that it's A inverse minus some other AR inverse A plus A, the inverse of that. So it becomes the difference of two inverse of matrices.
So before introducing the matrix inequalities, I want to present a very interesting definition and theorem, which we can use it to approximate where the eigenvalue of matrix are, which called Gershgorin disk and the Gershgorin disk theorem. So let A equals to Aij be a complex invariant matrix for I, which for I belongs to 1 to n. Let Ri be the sum of the absolute value of the non-diagonal entries in ith row. The Gershgorin disk, which is centered at the diagonal AII with radius I, is equals to di, which is equal to z belongs to C. The absolute value of z minus AII is smaller or equals to Ri. And the theorem of Gershgorin disk is every eigenvalue of a matrix lies within at least one Gershgorin disk. So next, I will give you an example of how can we use a Gershgorin disk to find the eigenvalue. So if we have a matrix M, which is 5, 1, 3, 3, 6, 2, and 4, 3, 9, then we can find Gershgorin disk by the definition, which the D1 is z belongs to C, and absolute value of z minus 5 is smaller or equals to 4, and D2 is also like that belongs to C, and that absolute value of z minus 6 is smaller or equals to 5. And then we can use the definition of Gershgorin disk to find the formula of the D3. And then I draw the disk for Gershgorin disk for M, and I will use a pen to note something. And we can easily find that the okay, can I use it? Yeah, I think I can use it. We can easily find for disk 1, which is the purple disk there, the standard is at 5, and the radius of the disk one is like 4 there, which is just based on the equation of the Gershgorin disk of D1. And then we can like find I'll clear it. And then we can find that the D2 is the blue disk there, and the center is at 6, and the radius is 5. Like this. And for the last one, the D3, the center is at 9 there. Oh, I think this one will be 9. And like, as we know, the radius is 7. So it's like this. And by the Gershgorin disk theorem, every eigenvalue lies within at least one Gershgorin disk, and which we like can draw the picture to show that. And finally, we can use the knowledge that we learned in the previous linear algebra course to find the actual eigenvalue of M. The first is 4, so we can find the 4 is in the Gershgorin disk. And second one is 2 times, okay, I will clean the 4 is there. And we can find another eigenvalue of M is 2 times 4 plus the square root of 5, which is approximate 12.5 is maybe is there. And the last one, the eigenvalue is 2 times 4 minus the square root of 5 is approximate 3.5. It's still in the Gershgorin disk. It will be there. There. So next, I will show the proof. Can you go to the next page? Thank you. Next, I will show the proof of Gershgorin disk theorem. Recall the Gershgorin disk theorem that every eigenvalue of a matrix lies within at least one Gershgorin disk. And here's some step of proof. Let lambda be an eigenvalue of A with corresponding non-zero eigenvector x, and suppose the absolute value of xi is greater or equal to absolute value of xj for all j belongs to I to n, which we can conclude that the xi has the largest magnitude. And we know in the previous linear algebra course that ax is equal to lambda x. Then we can use a sigma notation as the inner product of each row of A with x, and we focus on xi right now. So we got the following equation there. The ax equals to lambda x implies the summation of aij xj, where we take summation from j equals to 1 to n, which is equal to lambda xi, which implies that then we can subtracting aii xi for both sides, and we got the following expression: the summation of aij xj, where j is not equals to I, is equal to lambda minus aii times xi. Then we can like divide both sides by xi and take the absolute value of the previous expression, where we got the absolute value of lambda minus aii is equals to the absolute value of summation of aij times xj over xi, where j is not equals to I. By the triangle inequality, we can write the previous expression like the absolute value of the sorry, can I use it? This part is smaller or equals to the summation of absolute value of aij times the absolute value of xj over xi, where j is not equals to I, and which is smaller or equal to the summation of absolute value of aij since we know that xi is the largest term of x, so xj over xi, absolute value of xj over xi is greater than 0, but smaller or equal to 1. So we got, by the Gershgorin disk definition, we got the final answer there is like lambda, the absolute value of lambda minus ai is smaller or equals to ri. We have already proved the Gershgorin disk theorem there.
So, and the Gershgorin disk theorem has some application in physics, and the next theorem I'm going to present can be applied in mathematical statistics. So the theorem is the following. So B is a P by P positive definite symmetric matrix, and the small b is some positive number. And for all P by P positive definite matrix sigma, we know that 1 over determinant sigma to the power b times the exponential of that term is less than or equal to 1 over the determinant of b to the power b times 2b over e to the power bp. And the equality holds only for sigma is equal to 1 over 2b times the matrix big B. And in order to prove this theorem, we first introduce the matrix square root as we showed in the introduction part. So we use a matrix square root, and then we know that the trace of the sigma inverse b is equal to the trace of sigma inverse to the square root of b times the square root of b, since we can write b as b equals to the square root of b times the square root of b. And then by the property of trace, we know that trace xy is equal to trace yx. So the second equality also holds. And then we consider the eigenvalues of the square root of b times sigma inverse times the square root of b. And in the introduction part, we already proved that this matrix is positive definite. So we know that lambda I is positive for all I. And also we know that trace is equal to the sum of eigenvalues. And also determinant is equal to the product of eigenvalues. So finally, we get the sigma of lambda, like the sum of lambda I is equal to the trace of sigma inverse times b. Also, the determinant of sigma is equal to determinant of b over the product of the eigenvalues. And then to continue the proof, we first consider the left-hand side. We try to simplify it. And we use a result we've proved before. So we plug determinant sigma in and get it's equal to the product of eigenvalues over determinant b and raise it to the power b. And also we plug in trace. So it's equal to the negative e to the negative of half of the sum of eigenvalues. And then we use the property of exponent like e, and then the multiplication. So e to the sum is equal to the product of that. And finally, now it becomes a calculus problem. So the variable is lambda I, since the matrix is a random matrix. So all we need to do is to use the calculus to find out the maximum. So we can find out, we skip the detail here, but when lambda I is equal to 2b for all I, the function is maximized. And thus, finally, we get 1 over determinant b to the power b times 2b over e to the power bp. And also, since it only reaches the maximum when lambda I equals to 2b, so we know that the equality holds if and only if sigma is equal to 1 over 2b times b. And I previously say that it has application in mathematical statistics because by applying this theorem, we can find the maximum likelihood estimate of multivariate normal distribution by using this theorem.
Okay, next I will introduce the Rayleigh-Ritz theorem, which I previously used the Gershgorin disk to find the approximation of eigenvalue by draw the graph. And Rayleigh-Ritz theorem is a numerical method of approximating the eigenvalue, and it originated in the context of solving physical boundary problems. So the Rayleigh quotient for complex Hermitian matrix A and non-zero vector X is defined as Rax is equal to like X star AX over X star X. So if A is a real symmetric matrix, the Ra will become like X transpose AX over X transpose X. So the Rayleigh-Ritz theorem is like, let A be an n by n symmetric matrix with eigenvalue R1 to Rn, which we arrange them in increasing order. Then for X is not equals to 0, we have three following statements that Rax is bounded by the lambda 1 and where lambda 1 is a minimum of the eigenvalue and lambda n is the maximum of the eigenvalue. And we got the lambda n is equals to maximize all of X transpose AX over X transpose X when X is not equal to 0. And it's also equals to maximum of X transpose AX when X norm is equal to 1. And similarly for lambda 1, which is the minimum of the eigenvalue. And for the next, I will give you an example. Here we let we let a symmetric matrix A, where A is 1, 1, 1, 1, 2, 2, and 1, 2, 3. And we randomly pick the X, and I pick X1, which is equals to 1, 2, 3. X2 is equal to 4, 5, 6, and X3 is equal to 4, 6, 8. And then we can compute the Rayleigh quotient there, where Rax1, just apply the Rayleigh quotient formula there. We got Rax1 is equal to 5, and Rax2 is approximate 4.961. And for Rax3, which we got the approximation value, which is 5.034. And this gives the lower bounds for the largest eigenvalue of A, where we can compute the lambda 3, which is approximate 5.049.
And a generalization of the Rayleigh-Ritz theorem is a Courant Fischer theorem. I find this one like one of the most important results in matrix analysis. So the theorem is the following. So let A be a symmetric n by n matrix, and let lambda 1 to lambda n be its real eigenvalues. And let v1 to vn be the corresponding eigenvectors. And for any k, we let S0 to be the set of 0, only contains 0. And we let sk equals to the span of v1 to vk. And also let sk perp be the orthogonal complement of sk. And then lambda k is equal to the minimum of x transpose ax when x has unit length and also lies in the xk minus 1 perp. And it also equals to the minimum of x transpose ax over x transpose x when x is non-zero and also in the sk minus 1 perp. And the proof is the following. Since A is a symmetric matrix, as we showed in the introduction, we can let A equals to Q lambda Q transpose be the spectral decomposition, where Q is an orthogonal matrix. And since orthogonal matrix preserve length, we know that the norm of Q transpose X is equal to the norm of X. And then we know X transpose AX, we can write it as X transpose Q lambda Q transpose X, which is Q transpose X transpose lambda Q transpose X. And by the equality before, we know that we just need to consider the case when A is a diagonal matrix. So we let A be lambda 1 to lambda n, the diagonal matrix. And then we can simplifies the quadratic form x transpose ax to the sum of lambda I xi squared. And since A is a diagonal matrix, we know that an EI is an eigenvector corresponding to lambda I. So then if x lies in the orthogonal complement of sk minus 1, we know for all I from 1 to k minus 1, x is orthogonal to EI. So their inner product is equal to 0. And thus xi is equal to 0 for all I from 1 to k minus 1. And then when x has unit length and also lies in the orthogonal complement of sk minus 1, we compute the quadratic form by the results before. It's the sum of lambda I xi squared. And x1 to xk minus 1 are all 0. So the first k minus 1 term just vanish. And then we also know the eigenvalues has the order. So it's greater or equal to the sum of lambda k times xi squared. And lambda k now is independent with the summation, so we can put it outside. And we know that x has unit length, so the sum of xi squared is equal to 1. So finally, it equals to lambda k. And also when x is exactly equal to ek, like the equality holds, x transpose ax is exactly equal to lambda k. Thus, lambda k is equal to the minimum of x transpose ax when x has unit length and also lies in xk minus 1 perp. And similarly, we can prove that lambda n is equal to the maximum of x transpose ax when x also has unit length. And then there's a theorem, which is a corollary of the Courant Fischer theorem. It's called the interlocking eigenvalue lemma. So the interlocking eigenvalue lemma compares the eigenvalue of the original matrix with the eigenvalues after adding a rank 1 matrix. So we let let lambda 1 to lambda n be the eigenvalues of A, and then let mu1 to mu n be the eigenvalues of A plus BB transpose, where B is a vector in Rn. Then the eigenvalues have this relation. And let's look at an example. So we let A be the identity matrix and B be the matrix, like vector 1, 2, 3. Then we compute A plus BB transpose to be that matrix. And since A is the identity matrix, we know that all the eigenvalues are 1. And by the interlocking eigenvalue lemma, we know mu1 is bounded below by lambda 1 and bounded above by lambda 2. So mu1 has to equal to 1. And similarly, mu2 also has to equal to 1. And also we know that the sum of eigenvalues is equal to the trace. So we can compute mu3 by using the trace minus mu1 minus mu2, which is equal to 15.
Okay, next I will introduce our last matrix inequality, which called the Weyl's inequality. In mathematics, an eigenvalue perturbation problem is that of finding the eigenvectors and eigenvalue of a system that is perturbed from one with known eigenvectors and eigenvalues. This is used for studying how sensitive of original systems of systems eigenvector and eigenvalues are to change. So if we want to know the change of eigenvalue of a Hermitian matrix that is perturbed, we can apply the Weyl's inequality. So the Weyl's inequality is that let A be n by n Hermitian matrix such that the eigenvalue of A, B, and A plus B are lambda IA, lambda IB, and lambda A plus B, arranged in an increasing order, respectively. Then for each k belongs to 1 to n, we got the inequality there is like the lambda lambda KAB is bounded about by the lambda KA plus lambda 1B and bounded by the lambda KA plus lambda NB. So the one consequence of this inequality is that the spectrum of Hermitian matrix is stable with respect to the small perturbation. It's at very small matrix B that the eigenvalue doesn't change a lot, which is, we call it stable. And when K is equals to 1, we have that lambda 1A plus B is bounded by the lambda 1A plus lambda 1B and lambda 1A plus lambda NB, which we can notice that for the first two term of the matrix, inequality, which is very interesting, that the lambda 1A plus lambda B or lambda 1B is smaller or equal to lambda 1A plus lambda 1A plus B. And for K is equal to N, we have the very interesting result as well, is we can focus on the last two term, that lambda N A plus B, which is smaller or equal to lambda N A plus lambda N B. So next, I will introduce how to prove our final Weyl's inequality there. So this proof step is very easy. It's just the application of the Rayleigh quotient and the Courant Fischer theorem. So for any x belongs to say n, where x is not equal to 0, by the Rayleigh quotient theorem, we got the lambda 1b is smaller or equals to rbx and smaller or equal to lambda nb. That's for any k belongs to 1 to n, and we let si be the random vectors. We got the following expression is lambda ka plus b, we equals to min max of the x star a plus bx over x star x, and we can divide the a plus b into next step. We got like this, and I will use a pen here. We got the next step for this is equals to x star min max x star a x over x star x plus x star bx over x star x. And this is the min max part is the general form of the Courant Fischer theorem. And for the next step, we apply the lambda 1b there. Since we got by the Rayleigh quotient theorem, we got this, in which we have the greater or equal to sign there, which we got our final answer, which is lambda, which is equals to lambda ka plus lambda 1b. And we finished the proof of the, I think for the first two term of the Weyl's inequality. And similarly, we can go to that. Similarly, we can do the last two term, which is lambda ka plus b is smaller or equals to lambda ka plus lambda nb, which we just apply the same theorem, and we got and apply the lambda n b part, which is greater or equals to that rbx, and we can have the similar result, which is the lambda ka plus b is smaller or equals to lambda ka plus lambda nb. So we have finished the proof of the for the Weyl's inequality there. So next, Zhekai will introduce some reference and some good books that we use in our lecture.
Yeah, so I first recommend the third one, like the Handbook of Linear Algebra. So this is a book covers both theory and application of linear algebra. So for the application part, it covers optimization, statistics, and also economics, combinatorics, and computer science. So for the application in combinatorics, it's specifically cover like spectral graph theory with some details. And for the application in economics, it cover some theory about application in game theory. And for the application in computer science, it cover a lot of numerical analysis. And for the optimization, so we can also further read the linear and nonlinear programming textbook. So this book covers both linear and nonlinear optimization, and especially the convex optimization in the nonlinear programming. And for the statistics part, I recommend the second one, which is applied multivariate statistical analysis, which is also an important part of theoretical statistics. And I think people with different background and different area of interest can all benefit from this list of reference. And I highly recommend the first 3 books. And that's all for our presentation. Yes, thank you very much.
Thank you.
Awesome. Thank you very much. That was an interesting, very informative presentation. I'm going to ask that people hold off on questions. So I'm going to put something in the chat. There's a Google form that we'd like you to fill out. This presentation is part of their work in a independent study project. So we'd really, really appreciate some feedback. So let's take a 3-minute pause, and please fill out this Google form in the chat, and then we'll take questions at 11:55. Oh, and for our speakers, feel free to get up, grab a glass of water. You guys did great. Thank you for that.
Yeah, thanks.
Thank you.